Afternoon and welcome to this webinar on SuDS in West Yorkshire, or Sustainable Drainage Systems to give it the full title. My name is Russell Bowman, and before handing over to our first panellists, I will briefly introduce the webinar and run through housekeeping. So it's clear we need SuDS to work in the UK, and flooding is how the UK faces up to climate change, and it's costing the UK billions annually. To put this in context, subsidence, the most damaging geohazard in the UK, is estimated to have cost the UK economy 3 billion over the last 10 years, whereas in 1 year alone, the 2015-16 winter floods cost over half this, an estimated 1.6 billion. Going forward, we need to manage flood risk and adapt to these increasingly extreme climatic conditions. SuDS will play a central role in this. And so we're here today to discuss the infiltration systems specifically. These sit at the top of the drainage hierarchy and therefore should be the first design option we consider. But why does getting them to work seem to be so hard? This webinar has been designed as an introductory session around this question, where each panelist will be given 5 to 10 minutes to introduce themselves, their role in the design process, and discuss what challenges they face and how they see them overcome. Q&A will follow with the remaining time. During the session, please post any questions you have to the chat feed and select for all panelists so we can see them. These will be selected for discussion during the Q&A or answers provided in minutes following the webinar. Similarly, certificates of attendance and an info sheet on site investigation for infiltration will also be emailed to you after the event. If sufficient interest, we hope to be able to follow up today with more specific talks on the various themes and ideas discussed. Finally, this is a brave new remote world we're operating in, as we're all probably familiar with. And so we do have technical support today, but if the session drops out entirely, we will record offline and share it around. So that's me. If I could invite Ed Norfolk from Bradford Council to kick us off with a bit of context on this session. Thanks, Eddie.
Right, okay. Thanks, Russell, for that introduction. So yeah, I'm Ed Norfolk. I manage the drainage team at Bradford Council. Before I came into this role, I worked in private consultancy, working on the other side, as they say. So I've got a bit of experience in both trying to design, but also now approving SuDS systems and infiltration systems. So yeah, as Russell's outlined, we're here today really to start at the top of that hierarchy, looking at how we, well, the challenge around draining surface water into the ground, essentially. That's like the first point of call that we're always looking for in any drainage strategy or system. And not wanting to tell people too much that they already know, but we all know sustainable drainage systems have been around for a long time. It's a way of getting natural water processes to work with modern drainage methods to ultimately mimic what's already happening in the natural water cycle. So that helps with stormwater surges, overflows, soil percolation, biofiltration, and just generally the natural water cycle. So it's obviously something we're trying to promote as much as we can, but it's a difficult one, especially in West Yorkshire, due to the undulating topography that we have, but also the variable ground conditions that we face. And I think a couple of the panelists will go on to speak about the challenges around assessing those ground conditions and the challenges around those. So yeah, that's one of the issues. There's obviously lots of other issues with SuDS, which we spoke about on many a time. I have meetings with other local authorities in the area, talking about how to promote these types of drainage systems. So you've got the adoption, maintenance, is it providing the right amenity, water quality issues? So yeah, but today we just want to talk about the infiltration into the ground part of the SuDS system, because I think that does have a big effect on all the other aspects of the perfect SuDS. So SuDS C753 as the 4 pillars of the perfect SuDS system: water quantity, so controlling the flow and volume, improving water quality where possible, providing amenity, and providing biodiversity benefits if possible. So to get all those four things to work, I think the infiltration part of that is a big aspect, to be fair, because a typical example which you might have in West Yorkshire, and I'm sure a lot of the other local authorities dialed in will agree with this, infiltration is usually discounted fairly quickly for a number of reasons, mainly ground conditions or topography. And again, panelists after me will probably speak about how that could change, how it could challenge those sort of assumptions and decisions. So you've got no infiltration, you end up with a reduced discharge rate to a sewer or to a watercourse, and then you'll end up with probably a large attenuation requirement on a development site then. And due to the topography or the layout or anything else, that attenuation usually ends up underground in a big concrete box. So out of those four pillars that we were trying to aim for, we've probably only achieved one there, which is the water quantity. And there's an argument to say that we're probably not reducing the volume of that water either. It's only the flow that we're controlling, which again leads to other issues downstream to the receiving networks. So yeah, why is that important then? Why are we interested in all that? From a local authority strategic point of view, I think Russell outlined it extremely well there in the introduction about the national challenge, but some more detailed stuff which I tend to deal with, for example, is the overloading of existing sewer systems. And obviously, it's not a local authority brief that Yorkshire Water obviously picked that up, but from our point of view, we really want to reduce the amount of surface water that ends up in these sewer systems for a number of reasons. One, they're all combined systems usually, especially in Bradford. I think that's pretty typical around West Yorkshire. And then you've got the CSOs which come off of those. So you load up the combined system with surface water. This loads up the CSOs. They've all got permits. They're all there. They've all, they're not doing anything they shouldn't be doing, but naturally they're there for good reason, to stop people flooding with effluent. But the more and more we put into those systems, the more times their CSOs are going to spill, the more times there is a risk of environmental impacts, etc. So yeah, dealing with the water at source would reduce the amount of surface water into those systems. Climate change, obviously, and resilience around flood risk is a massive aspect of our work, especially in Bradford and West Yorkshire. We need to always cater for that. And again, dealing with water at the source is one big way of tackling that challenge. Not so much an issue with water resources, but recharging groundwater levels. We're not got there yet, but there's obviously changing times to come, periods of drought, but also recharging groundwater levels for areas where they might be using, the water supply on the ground for potable water, etc. But also to improve biodiversity and amenity. We want to keep those rivers flowing if we do have times of big drought. Yeah, just like clarify that managing rainfall where it lands is a massive part of reducing flood risk. If every development site managed to do that effectively, I probably won't have a job, and but would also have a massive reduced amount of flood risk in the region. So just going through what sort of policies we have now in the authorities for trying to encourage this. So all local authorities will have some form of sustainability policies in their local plans. Most mirror what's described in the building regulations, that infiltration is the priority when you're looking at surface water management. We've got the MPPF, which was revised to try and encourage the use of SuDS. But again, that's only for major developments, 10 dwellings or more. So you've got SuDS as a priority, but then they've also got the caveat saying it's unless demonstrated to be inappropriate. So we've got challenges there. West Yorkshire authorities all worked together with West Yorkshire Combined Authority. Actually, we've produced some guidance which I'm sure most people have seen, but that gives you some good guidance on what information is expected if you are looking to apply for planning, from pre-development pre-planning, right through to reserve matters if you've gone down that route. And it's and I think we'll touch upon this about the importance of getting detailed information on the site at an early stage, so you can understand the characteristics and design the right drainage system, the right infiltration drainage system, hopefully. So yeah, that guidance is out there on WICA's website. I think we've got a link on ours, and it just goes through what sort of information we'd expect at different stages. And I think some people aren't surprised at what level of information we would really like to see. And then you've got Yorkshire Water, obviously with Sewers for Adoption 8th edition, promoting the use of SuDS. I'm not entirely sure how much is happening with that just yet, but yeah, that's another massive positive that we'll hopefully see some more come through with an adopting authority, which can take on those systems. And just quickly, some of the challenges, especially around this subject, you've got a lot of non-major developments which kind of fly under the net, so 9 houses and below, which are big developments. You get a range of different sort of information depending on the type of development and what sort of consultancy services the developer has asked for. But yeah, we're looking at issues a lot of the times with the testing. Really, it's the ground condition testing. We need to understand exactly what's going on that site, and how that is then portrayed to an approving authority is difficult. So I think I've discussed in the past with many people, truly understanding the hydrogeological regime of a site. So not just understanding if the water can disappear quick enough, but where does that end up? Because we as a local authority have to live with that potential decision for a long time if issues arise from it. So this is where good quality site investigation and monitoring in early stages is essential. So I don't want to take any Russell's thunder, so I'll pass on to him. I'm sure he'll be able to discuss that in detail. Thank you.
Russell, if you could unmute yourself, please. Thank you.
Apologies. Thanks, Ed. Yeah, really great introduction there. Thanks very much for that. And yes, so hello again, everyone. My name is Russell Bowman, as I said before, and after studying earth science and hydrogeology at university, I've spent 15 years working in the site investigation sector. 14 of those years were spent within a growing engineering practice. And as one of the early graduates into what I describe as the contaminated land era, I look back on my time in an engineering practice as being instructional. In short, if there was any questions remaining about the grounds or the SI, the engineer could just walk over and grill you. Less ominously, there was an exposure to the design process that independent site investigation firms don't generally get. And I mentioned the contaminated land era as pre-2000 or thereabouts, when Part 2A of the Environmental Protection Act came in. The site investigation would often be overseen by the engineers on the project, not the geoscientists. So my role in the process, on our typical development project, as the investigator, I'll be approached to provide a desk study. The focus of this report is invariably contaminated land, given the focus of the planning condition. It's an important point I'll come back to again. Around the same point of the project, a drainage strategy will often be required, and the drainage engineer will seek to answer two questions through that which relate to the ground. Firstly, what's the infiltration like on the site? And second, when can I have an infiltration rate? If not coming directly from the drainage engineer, then the second question can often just become how much for a BRE 365 test and when can you do it? So what are the challenges in that process? And this kind of relates back to the context that Ellie's mentioned there. So firstly, the challenge of uncertainty. I think the whole process and purpose of a site investigation is to answer questions about the ground that the design asks. This should be focused on processes focus process, addressing specific questions such as what foundations can I use, what materials will be present in the ground, and can I reuse them, what hazards are present and what risks are attached to them. For infiltration, the question is often framed as, what's the infiltration potential on the site? Now, as I said, at the desk study stage, the answer to this can often be low, medium, or high, with the answer commonly cribbed off of BGS or Environment Agency source data for the geology. Now, I have to admit, I've done that myself, and I'd say, as an investigator, that's a defensible position and appears to answer the question. Coupled with this, the investigator may have experience supervising BRE 365 tests in low permeability situations. Now, it's kind of fancy way of saying just watching water sit there in a pit. Through that, the value of the test appears to be limited to the investigator, and I think sometimes that can actually undermine their confidence in the process. Rather, I think what the designer is actually asking of the investigator is, what is the hydrogeological regime of the site? As Ed touched on, what are the constraints to infiltration, and where might be the best to locate the infiltration system? An important point to clarify here is I think the investigator should not be passing judgment on the suitability of the site for a given infiltration system. And this often comes up in reports, and I think exposes investigators to liability, and also I think guides or rather stops the conversation on infiltration quite quickly, whereby somebody will say there's low infiltration potential and soakaways are therefore not considered viable. I think they should rather be enabling the designer to take a more informed decision over that, because ultimately the investigator is not embedded in the design process and is not that familiar with exactly what the system is going to be on site. So as a solution to that first challenge of uncertainty, I think the designer should ask the investigator to advise on the hydrogeological model for the site, as Ed touched on again. If a geoscientist is likely to be the case, this task is one the investigator will likely have been specifically trained for through their studies, and it's common to other aspects of the investigation process, such as conceptual site modeling for contamination, or even detailed groundwater risk assessment. In turn, I think this would boost engagement with the process and offer the designer a more complete picture of the site. Secondly, the challenge of timings and cost, really. Given the drainage strategy often calls for on-site testing or ground investigation at the point when the investigator is reviewing historical and geological maps, does present a bit of a clash in timings. And while calling this a challenge might appear like crying over some spilt milk, in practice, I don't think it is, as the cost, risk, and logistics of doing an infiltration test can easily make up a major portion of the overall site investigation costs. As an investigator, this seems to be the most obvious pinch point in the process with clients for whom the design team ultimately all are working for, regularly pushing back on the need for this. So yes, some will have their eyes firmly fixed on the bottom line, the cash prize of the development, but overall, I think this feedback is valid and actually worth listening to. So again, for the challenge of timings and cost, I think again, the same solution applies. If through that desk study process, the investigator can actually offer a hydrogeological model, then the basis of the testing can be much more clearly justified. Finally, the challenge of testing itself. And this is a challenge that relates to the previous two challenges that we've just covered. And I think investigators can relate most strongly to this one. So hydraulic testing of any description is an involved, intricate process, and one that calls for a proper understanding of exactly what the test is measuring. The BRE 365 infiltration test, which I see commonly asked for and talked about in the context of infiltration to ground, is a field test. And I think it's in the same league as a zone load test or a skip load test to check consolidation and fill. And I mention that just to give you a sort of scale of the importance of this test. On its own as well, it offers very little data for a lot of cost, risk, and logistics. That is not to say that the data doesn't justify it, but it often doesn't For example, the test or tests will often be performed away from the location of the actual infiltration system at depths that don't tie in with the actual drainage level. And so invariably will have to be repeated when the design is actually finalized. They may be performed over a day, not allowing sufficient time for repeat testing, something that again would add more cost, risk and logistics. If the BRE36 test is considered a field test rather than just a general part of site investigation, then it stands that it should be performed in the ground drainage system location at depths reflective of the actual invert level or the drainage level. And so then what can we do if we're going to pause this test until the system is designed, or test and retest once designed? I think it's seems like a bit of a chicken and egg situation, but again, I think if the investigator is able to develop a hydrogeological model, this would offer much more clarity needed to inform a design. Likely infiltration rates can be estimated from literature values, and the behavior of the infiltrating water can be discussed. Any field testing done should be reflective of the system's design, but other tests such as small-scale percolation tests laid out in BS 6297 or the Part H method, as some people call it, simple classification tests in the lab like particle size distribution, all can be undertaken at relatively little cost, but feed into a lot of data into the hydrogeological model and then enable follow-on decisions around larger scale tests like the BRE3651. So just quickly, just to summarize those points, I think to the designers, I would sort of ask you to ask your investigators to advise on the hydrogeological model for a given site, ask where the water will go once it's infiltrated, and if you have an idea of the design early on, discuss those with the investigator so they can be clearer about exactly where the test needs to be performed. And specify the 365 test when you know the likely location of the infiltration system so it can be much more valuable. And so the investigators engage that hydrogeological knowledge that you are likely trained for and present a hydrogeological model to designers. Familiarize yourselves with the different hydrogeological parameters, such as the percolation rate, VP, infiltration rate, F, the design infiltration rate, Q, D10 for particle size distribution, and K for permeability. An info sheet will summarize these for those in attendance. They all interrelate to one another, but quantify slightly different parameters. Last 2 points, ask questions about the design. Where's infiltration happening? What is likely to happen to that water? And also, crucially, I think, where the infiltration system is designed to maximum extent that is practicable and safe. And so even if you're getting 10-6, that may still offer a useful capacity to the overall drainage strategy. Bit of a whirlwind, but thanks for bearing with that. I'd now like to invite Richard Barson from Leeds City Geotechnical Section to kind of follow on in the role of an approver or a designer in that process.
Thanks, Russell. Just for a bit of background, I've worked for Leeds City Council Geotechnical Section for about 16 years, previously in a private consultancy. In that time, I've spent a long time on site doing soak-away tests, watching them and thinking about them. Our current work is various roles. We act as the investigator, the designer, and also the regulator, depending on the project. And that's mainly working for Leeds City Council, but also other external clients. As part of our investigator and designer roles, we carry out feasibility assessments, soak-away testing, soak-away design, and flood risk assessments. We also design remedial works to address existing flooding problems. In our regulator role, we provide technical assistance for planning applications, highway adoptions, and other developments. For example, schools, parks, things like that. This generally involves checking calculations for soil infiltration rates and soak-away designs. I've been asked to discuss a few practicalities and challenges in terms of testing and designing infiltration systems generally. The first thing that we always check is the presence of mine workings and mine shafts. This is a particular problem in the West Yorkshire area, and unfortunately it's not just coal. There are also mine workings in our area specifically related to sandstone extraction, ironstone mining, sand, the basal Permian sand in our area, and also fire clays. The main difficulty with soakaways or infiltration systems is if they're installed over mine workings, they may initiate a collapse. Some of them can be quite spectacular. Another common problem is groundwater regimes are often not established with confidence by ground investigations. The guidance states that generally there should be a metre of unsaturated soil beneath the base of the soakaway, and that seasonal fluctuations in groundwater level should also be taken into account. Other problems can result from the field testing that's been carried out. A very common problem with this is that insufficient water is used in the tests. So again, the guidance states that where the area to be drained is greater than 100 meters squared, the volume of water used in the test should be at least a cubic meter, 1 cubic meter, which is quite a lot of water. The testing, as Russell mentioned, must accurately recreate the proposed soakaway construction. So it needs to be in the specific location of the soakaway and carried out at the correct elevation. Again, as mentioned by Russell, repeated tests are generally required. The BRE guidance states that this should be 3 consecutive tests carried out on the same day. I would like to point out that generally falling head tests in boreholes are not appropriate, but can be used to supplement full-scale soakaway tests. The exception here is when designing a specific borehole soakaway scheme. The next issue, which is more problem with housing developments, is the available space for SuDS. Generally, housing developers want to maximize their development area, and this can leave insufficient space for soakaways even if they work on the site. Generally, no soakaways should be sited within 5 meters of any structure, specifically buildings, retaining walls, things of that nature. There should be no soakaways designed sort of sited beneath the highway footprint, which is a common issue we see. For clarity, this presents a number of maintenance issues. Often there is only one site access, and quite often these soakaways are sited beneath the road. From a local authority's perspective, we need to assume that eventually the soakaway will fail and it will require full excavation and replacement. And it's just not practical if that excavation will require completely blocking the estate road access. Generally, we do not permit, and this is Leeds City Council specifically, we do not permit soakaways to be sited within 5 meters of a highway footprint. The adoptable width in this case includes the footways on either side, primarily because soakaways can induce settlement around them. The land where the soakaway is sited must also generally include an easement in all directions around the perimeter of the soakaway to allow for future maintenance. Typically, this is 5 meters, but it could be reduced in certain circumstances. If the soakaway is to be adopted by the local authority highways, the land where the soakaway is sited must also be adopted. Generally, it's not practical for the land to remain private, and this is purely linked to maintenance. Potentially, we may need to access the site with very little notice, and we need to have free access to that. On a scheme where multiple soakaways are being proposed, these must also be sited at sufficient distance apart. I believe the Syria guidance states 5 meters. Made ground is a very common problem on sites, and although infiltration testing is usually successful in made ground soils, it is almost never appropriate. The main reason is that the discharge of these accumulated waters is quite uncertain, and you can actually cause flooding of adjacent sites. The introduction of additional water into these soils, these made ground soils, can also mobilize contamination and can pollute the groundwater or watercourses. The main issue is introducing water into an unsaturated, poorly compacted fill material can induce collapse compression, which leads to fairly large scale settlement of the surface, which would be unacceptable generally. Slope stability issues must also be considered, particularly where you have unstable soils, and unstable soils can comprise made ground soils. They can also comprise natural deposits, landslips, or head deposits. There's a few issues with the design of a lot of these soakaways as well, from my experience. There's 2 methods in which you can design a soakaway. There's the BRE 365 method, or there's the Syria C156 method. But the design assumptions are quite different. The BRE 365 method assumes that the base of the soakaway will silt up and become ineffective long term, which is realistic, I feel. Whereas the Syria method includes the base area, but acknowledges that the base will silt over time and consequently applies a factor of safety to the design. And the most common mistake that we see as in our regulator role is that the Syria method is not applying the correct factor of safety to the design. Generally, for private soakaways, the factor of safety applied should be either 3 or 5, and for adoptable soakaways, it should be the factor of safety should be 10. Again, I cannot think of an example where I have seen the correct factor of safety being applied to a design at the first stage. So what advice would I give to anyone coming into this role? Make sure you understand and have read the BRE 365 and Syria 156 documents, and make sure you have a high quality ground investigation.
Fantastic. Thank you very much, Richard. That was very detailed. I'd now like to invite Joe O'Meara and Steve Bowles to talk on a new innovative infiltration system that they're both involved with.
Good afternoon, everybody. I'll kick this off just with a brief introduction to the GD90 product. My name's Joe O'Meara, Director at Groundwater Dynamics. We were incorporated in 2012, and in September of that year, we introduced the GD90 to the UK market after seeing the product in action in the US, where it basically drained a swamp at the end of Detroit International City Airport in solid clay. So seeing was believing, and we took it back into the UK. The first installation we had in the UK was field drainage. It was draining a practice ground for Edgbaston Cricket Club. And our first objective was to test the product as a general, I call it field drainage product, where it was getting rid of standing water, surface saturation, etc. The installation at Edgbaston Cricket Ground was also tested by STRI, the Sports Turf Research Institute, who advise on a lot of international football pitches on drainage. And their test showed that ground that was previously infiltrating at less than 1 mil an hour, 1 year post the installation, was now draining at 6 mil an hour. And in the wettest corner, where the flooding used to occur and block the entrance, where water was also running off a car park into that area, the best recorded rate of infiltration in that area was 43 millimeters per hour. Their report that followed their investigation classified the system as a primary drainage system. So not a secondary system, primary system where it did not have to rely on other systems in order to work effectively. So that for us was a real win-win situation that got some press coverage and got us out of the blocks in terms of draining sports pitches and generally dealing with heavily saturated and flooding ground. One of the other things about the system is that although we drill micro boreholes up to 12 meters, this conversation came out with a meeting we had with SEPA in Scotland. It's not typically a borehole drainage system, because once the GD90 devices are vertically installed, the borehole is capped with at least 300 millimeters of native arisings. And the water finds the system laterally. It doesn't go into the borehole vertically as would a borehole system. The installation of the system is non-disruptive, and that can be demonstrated when you take a look at Ascot Racecourse. The parade ring was flooding, one half of it was flooding, and we installed there between the barriers that surround the ring and put an effective drainage system in to stop that happening. And you'll see from our website, we've installed at Glen Eagles on golf greens, and come off, and 2 days later the golfers are back on there playing golf. So we have a system here that unlike a lot of drainage systems where you think of lots of trenches and soil being moved around, we can actually install a system without that huge amount of disruption. So until 2015, primarily we were installing a drainage system, and we were invited to sort out people's worst nightmares where they'd tried other things and failed. And we were invited along and managed to put systems in that would sort those problems out, until we came across in 2015 Newcastle High School for Girls. It was a project by the Girls Day School Trust. A new school wanted an all-weather hockey pitch for the girls, and Newcastle City Council were involved, as were Northumbrian Water. The micro drainage on the site showed that the requirement for attenuation was 530 cube. And the only solution at the time we were introduced was for tankers to come along and remove water from underneath the attenuation crates. And there was about 300 of those required every year. So this is where we first started infiltration testing to see, to start measuring infiltration rates at depths up to 12 meters. And in that instance, with Curtin's engineers, we put together a drainage design statement that satisfied Northumbrian Water and the Newcastle City Council, and installed our first engineered SuDS drainage system at Newcastle High School for Girls, where a project that wouldn't have gone ahead otherwise was able to be completed with no stormwater leaving the site. There was no connection to any public assets, stormwater drains, or combined sewers. This really put us onto the map, because at the same time we realized that we'd succeeded in dealing with surface saturation and taking huge amounts of water off the surface. So the next step was to say, okay, let's create some infiltration trenches and use the trenches to buffer water to take it off the surface, and then install our GD90 devices 300 mil below the base of those trenches, which effectively is what we've been doing ever since, and supplying housing developers or any clients really who have a need to deal with their stormwater at source. I think we touched on this earlier on, that the real jewel in the crown is being able to deal with stormwater where it falls at source, and not have it being piped to another area or put into a water course or moved downstream to cause problems elsewhere, or indeed to be treated by a local treatment plant, which is where energy and money is being spent to effectively clean water. There are also a number of strategic uses of the product. We installed at East Midlands Airport at the end of the runway, where water was ingressing underneath the apron. So we can strategically put some defensive lines in the ground to stop groundwater, to reduce and to drop the level of groundwater underneath an asset. And that same design principle is used for dewatering basements. We've now successfully completed work where if you put a cordon of this product at 600 mil centers around an asset, it takes the hydrostatic pressure back away from the walls and will dry the asset out. So underground car parks, basements, and cemeteries, graves. We've done a lot of work with local authorities where they experience problems in their graveyards when they dig a grave and the grave fills with water. Obviously, very distressing for the families. So a number of those have been done with local authorities. To give you a few more examples, and Russ, you're going to have to tell me about time here, please. Flood alleviation projects, in particular smaller schemes where properties have been on the receiving end of upstream developments, where all of a sudden they find that water is ingressing into their properties or onto their premises. We've used a combination of defensive lines, infiltration trenches, to divert and take down the water and keep it away from the property. We're about to do another one of these, and you wouldn't believe the videos of this. This property is flooding, and it has a sump pump underneath the property with a periscope pump at the back. So sooner or later, it'll fall into a big hole in the ground unless something is done. Housing developments is now probably the mainstay, the largest part of our business, with applications for connections to public assets being limited or refused altogether. And we find certainly with some urban renewal projects that, again, by taking water down at source, we are making urban renewal projects feasible, economical, and projects are going ahead which otherwise wouldn't have. Also post-construction, where there are groundwater issues post-construction when all the drainage has been put in, but you find there's still problems. We do a lot of work with developers where we go in afterwards with a very light footprint and deal with remote areas. Obviously, no need to connect, so no digging up required. I think that the confidence we now have in the product is because we have so many different, over 300 reference sites across the UK, and the fact that we now have an engineered solution means that with the work we do on the hydrogeological reports before we go on site, with the infiltration testing we do, we take every effort to make sure the system does not conflict with any planning regulations. It certainly isn't a solution for everything, far from it. But it has its place, and where it's used effectively, it's a fantastic solution. We have, for the last 3 years, had PI insurance behind our designs for £2 million. And I think the fact alone that we have an engineered SuDS solution is giving more confidence in in developers using these solutions. So really, I think I'm about to pass you over to Steve Bowles, who has been involved from the outset with our design and developing this design forward, so that what we do actually fits into micro drainage and the industry speak, which surrounds soakaways and the type of work that we do. So, Steve, I'd like to pass over to you, really, just to give a broad brush on your role in the process.
Thank you very much, Joe. Thanks, that was a really good introduction to my part, I think. As Joe says, I was introduced to groundwater dynamics at Newcastle High School for Girls, where I was landed with an absolutely insurmountable problem from my point of view as a drainage engineer. I've been designing drainage for nearly 30 years, and I have to say, a client suggests that they can take nearly a hectare of land and tanker the water away. I didn't quite know what to say, but thankfully the guys at Groundwater Dynamics were able to show me a system that with a little bit of manipulation and a little bit of thought, we turned into a drainage system that I have to admit the client was over the moon with. I understand it continues to work really, really well to this day. May only be 5 years, but I'm sure at the time that we were designing it, there were quite a number of people who were expecting it to fill up and do nothing after about 3 weeks. So I'm happy. The people that are maintaining the system are happy. The client was absolutely overjoyed that they finally managed to get a world-class sports facility on their new school. But to go back to where this generated from in terms of design, yes, as Joe said, Newcastle High School, what we did was we basically undertook a series of boreholes and poured water down them. I see one of the comments through from one of the attendees earlier says something about might need to just do something a bit more than chuck some buckets of water in a hole. From Michael, yes. To a certain extent, yes, quite right. We do need to do a chunk more than that, and that's where we need to get the investigators involved to tell us where we should be throwing the buckets of water and what kind of holes we should be putting in to start off with. But realistically, once the groundwork's been done, once legwork's been done, once all the desk studies have been carried out, it does come down to finding out just how much water will go into a hole on site. Getting the right part of the site, getting the right depth of hole is quite critical too. And then it's just a question of juggling the numbers to make sure that you get the right answer. One of the beauties of the GD90 system is that it comes in any length you like. You can do short holes, you can do long holes, you can do tens of thousands of holes if that's what the solution requires. We have sites that we've undertaken successful installs on where there's been issues with depth of bedrock over part of the site. The idea is not to allow the surface water off the site, but to deal with it on site. But that doesn't mean that we don't sometimes have to move it around the site to get the most efficient way of disposing of it into ground. These things are all part of the design process. It isn't a panacea for all ills, but it is a very, very effective system, and it does have a vast number of uses. One of the things that we are still looking into and haven't managed to quantify as yet is the actual improvement over time that is experienced with the system. We base all of our designs on the idea of throwing water down the holes that we've drilled and measuring how long it takes to go away. This is then multiplied up, factors of safety applied. We run it through micro drainage to attain a volume of attenuation so that we can balance the inflow with the outflow for the impermeable area, part of the country, and the severity of storm that we're considering. But what we're finding is that that's a solution that shows how the system will work day one. It takes absolutely no account of the improvement in the system over time. The maturation period varies from site to site. It's largely governed by the cycles of wetting and drying, but also the types of material that it's going into. What tends to happen is that the micro boreholes decompress locally, and we create micro fissures radiating out from the devices that improve the infiltration interface capability of those individual boreholes. They aren't of such a size that it causes huge great depressions in the ground. I've not seen anything in the way of a depression forming around any of the devices ever. And this is partially because they are generally below ground level. We're talking about separation from pollution. So if there is a pollution incident, you can use your upstream treatment train to deal with that, keep it away from pollution into groundwater, and we can deal with all manner of things, largely just as it says in the SuDS manual. We are an ideal way, to my mind, of disposing of surface water in the vast majority of installations. I see Russ has just raised his hand and waved at me, so I guess I'm going over time. So I shall leave it there. But if anybody would like to speak at greater length, by all means, look me up. I'm sure my contact details can be made available. Thank you very much.
Thanks, Steve, and thanks, Joe. Hopefully, within these talks this afternoon, there's been some food for thought and possibly some appetite for follow-on discussion. Just quickly going on to questions in the last 10 minutes of the session. I see there's a few that have come through, so thanks very much for those who've contributed. Jacqueline asks, how do we establish the seasonal variations? Does this mean testing over the seasons? If I could ask Richard perhaps to kind of feed in there with his knowledge of the design and investigation.
Hi, yeah. In an ideal world, you would want to do testing over various seasons. In practice, the time is probably not on your side. So I would potentially argue that you are better trying to establish the groundwater levels during the winter months, because then they will probably represent potentially the highest levels. A really good example of this is alluvium deposits or river terrace deposits in the bottom of a valley. Because generally, if you were to investigate these in the summer months, you would find that these quite granular sands and gravel type deposits are free from water, and generally you can introduce almost as much water into them as you like and they will work fine. But then in the winter months, they are completely saturated. And this obviously would, it severely impacts on the feasibility of that scheme. And it's not necessarily about getting a full 12 months worth of monitoring data for every single site. It's just understanding where those variations are going to impact on your design, really.
Great, thank you, Richard. Hopefully, Jacqueline answers part of your question. And I think it's, again, comes back to the hydrogeological modelling and getting that set out early on. There's another question from Jamie who asks, I think this is a question for Ed, does SuDS retrofitting have to go through the planning process?
Well, I suppose the answer to that, it's not straightforward as usual, is it depends on the type of suds, the size of the suds, what you're looking at. I'd suggest always speaking to the planning department before doing any sort of engineering works, because it probably will fall under some part of it. You've asked there about suds being retrofitted to the highway. That's slightly different. A lot of highway improvement works might come under permitted development. So you might not need planning permission as such, but again, it's always helpful just to discuss that with the local planning authority before you intend on doing any retrofitting.
Nice one. Thanks, Ed. Yeah, Michael asks a question about sort of Wakey with regards to the groundwater dynamics or the GD90 system. Sounds like an interesting solution. Developers should consider before discounting infiltration. Does this offer treatment as well as attenuation, and would it be suitable on a primary aquifer, principal aquifer?
That's probably one for me, I think, Russ.
Yes, please. Yeah.
And does it offer treatment? Strictly speaking, no, it doesn't offer treatment. It's purely a discharge, is the way that we tend to look at it. And as such, yes, it would be suitable on a primary aquifer because there is no direct mechanism for pollution to get into the system. What we tend to look at is, in terms of a SuDS treatment train, we do a lot of work in Scotland where they apply the simple index approach, and the advice to all the designers up there is treat the GD90 as your discharge point. Don't rely on it for treating anything. There are things that we do with the attenuation trenches, such as wrapping in geotextiles to remove silt so that we maintain the volume in the gravels, using specialist geomembranes so that we can capture and treat hydrocarbons, using the silt, the gravel filters themselves to remove silts is fine, but realistically you'd want to have a silt trap or something smaller and more accessible upstream, where you aren't going to be messing with your discharge to capture all of those items and deal with those potential pollutants. So yes, from my point of view, I believe it is suitable on a primary aquifer. As with anything to do with aquifers, the EA would be involved. I am speaking to the EA on a number of our projects at the moment. We are going round and round in circles and doing quite a merry little dance in a number of different fashions. But I think all in all, the EA are going to get to the same position as SEPA got to a couple of years ago, in that actually this is a very good system and a very good idea.
Thanks, Steve. I think we've got 2 more minutes. There's one question, sorry, I just missed, from Paul, who's, I think this is probably for you, Ed, if that's okay. What are your opinions on the SSG Appendix C guidance for adoption of SuDS? Oh, you're on. Sorry, Ed, you're on mute.
Sorry. Can you hear me now? Yeah, so that's the SuDS sector guidance about, you know, the specification of drainage systems when they're getting adopted. I think it covers fairly well what we've been discussing, in particular this topic, and it points you towards SuDS, the SuDS manual, about how that testing of the ground should be undertaken prior to it being discounted as a suitable use for surface water discharge. It also highlights that on sloping sites, the impact of infiltration on neighbouring land should be taken into account. So that backs up again the need for a detailed site investigation with some establishment of the hydrogeological regime on that site.
But I think there's just one final question there, which we'll pick up in the minutes from the meeting, because I think if we finish now, we're bang on time. So it just remains for me to thank everyone on the panel today for coming along and sparing their time freely for this session. And I really hope that everyone who's attended or joined in has got something to take from this. And as I said before, hopefully we can follow this up with more specific theme talks on the different elements. So thank you very much, everyone, and good afternoon.